Good morning, everyone. So welcome to the Mars Through Time conference. So this conference will have been named Mars Climate Through Time. In fact, the origin of this conference is because we have had here a very big project.
Good morning,
by everyone. Welcome to the Mars Through Time conference. And it's about modeling.
Good morning.
It will have been named Welcome to the understand that we have
Good morning. Good morning.
Welcome to the Martian conference.
Good morning.
So what are the implications of each of these? So what are the implications of each of So what are the implications of each 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 So what are the implications of each
salt in this ice. And I think the best evidence for liquid water today, like probably right now, is the electrical conductivity measurements by Stillman and Grimm that basically show that even at these high latitudes, there's a few hour thin film of water that's consistent with the electrical conductivity measurements. I love this picture on the right from the rovers. So this is the Spirit rover dragging its wheel through a sandy patch. And it excavated this glorious salt deposit. So that means about this far beneath the surface, in sands, there are sulfur and chlorine salts and perchlorates as well, most likely, that are formed from the kind of process shown in the cartoon there on the right. And this cannot be billions of years old. This is recent. So how do we do this? Well, the mechanism is obliquity, and I think there's a great paper by Peter Buehler that I think needs that should be kiloyears down at the bottom, not million years, 500 kiloyears back in the past. What one sees is a 2 times increase in pressure. And at that point, all of the CO2 that was in the have been for that period of time pretty much witness plates, that they all come into existence at different points as the deposits are created, but then many of them have been sitting there on the surface for 3.5, 4 billion years, relatively undisturbed. So they've been experiencing almost all of the alteration. But I think in terms of the duration, it's pretty consistent with it being limited, and the fact that you don't, in materials that come into existence on the surface of Mars somewhere for that period of time, between pretty much 3.5 plates, they don't have that they all come into existence at different points, period of time, pretty much witness plates, that they all come into existence at different points. I think the other data point is, but then many of them have been sitting there on the surface for 3.5, 4 billion years, relatively undisturbed. So they've been experiencing almost all of the departure is, I think, but I think in terms of the duration, it's pretty consistent with it being limited, and the fact that you don't, because the temperatures are getting materials that come into existence on the surface have been for that period of time pretty much witness plates. They don't have that they all come into existence at different points, period of time, pretty much any water at all. That they all come into existence at different points. I think the other data point is, but then many of them have been sitting there on the surface for 3.5, 4 billion years, relatively undisturbed. So they've been experiencing almost all of the alteration. But I think in terms of the duration, it's pretty consistent with it being limited, and the fact that you don't, because the temperatures are getting materials that come into existence on the surface have been for that period of time pretty much witness plates. They don't have that they all come into existence at different points, period of time, pretty much witness at all. That they all come into existence at different points as the deposits are created, but then many of them have been sitting there on the surface for 3.5, 4 billion years, relatively undisturbed. So they've been experiencing almost all of the alteration. But I think in terms of the duration, it's pretty consistent with it being limited, and the fact that you don't, because the temperatures are getting materials that come into existence on the surface have been for that period of time pretty much witness plates. They don't have that they all come into existence at different points, period of time, pretty much witness plates. That they all come into existence at different points as the deposits are created, but then many of them have been sitting there on the surface for 3.5, 4 billion years, relatively undisturbed. So they've been experiencing almost all of the alteration. But I think in terms of the duration, it's pretty consistent with it being limited, and the fact that you don't, because the temperatures are getting materials that come into existence on the surface have been for that period of time pretty much witness plates. They don't have that they all come into existence at different points, period of time, pretty much witness plates. That they all come into existence at different points as the deposits are created, but then many of them have been sitting there on the surface for 3.5, 4 billion years, relatively undisturbed. So they've been experiencing almost all of the alteration. But I think in terms of the duration, it's pretty consistent with it being limited, and the fact that you don't, because the temperatures are getting materials that come into existence on the surface have been for that period of time pretty much witness plates. They don't have that they all come into existence at different points, period of time, pretty much witness plates. That they all come into existence at different points as the deposits are created, but then many of them have been sitting there on the surface for have been for that period of time pretty much witness plates. That they all come into existence at different points, period of time, pretty much witness plates. That they all come into existence at different points as the deposits are created, but then many of them have been sitting there on the surface for. It's a one-way trip after, whatever pummeling phase happened between, 4.1 and 3.8. Pick your favorite date. But from pretty early onward, 3.8 onward, there's really not a mechanism that once that water gets sucked down into the crust, there's not a mechanism to pull it up. So once volcanism stops putting new water into the system from the release of the mantle, you only have that one way down to the crust and lost to space. There's not really a recycling mechanism for the clay minerals.
Thanks.
It's a one-way trip after, whatever pummeling phase happened.
Thank you very much, Bethany. I'm very enthusiastic about this idea of the fate of the atmosphere and so on. But I have a comment about recent Mars, and I think I would like to be. I think we should be more careful about the idea that liquid water is easy to form and that you can carve the gullies and so on. as you suggested. And in fact, for instance, you refer to the Dixon et al. Paper. The Dixon et al. Paper use our model here, but it's wrong. They just do it wrong because they neglect, for instance, sublimating cooling. I want them. It's this way. But so Luc Allange this week will elaborate more on that and the fact that it's really, really difficult. And I think it's not, you have to be super careful before thinking that liquid water can play a role. And for instance, for the gullies, of course, as you know, we have plenty of evidence that CO2 ice, sublimating CO2 ice is fluidizing when it sublimes the grains and creates things. You also have to remember one thing is that all these gullies are formed on icy terrain, of course. Coming from the past, it's ice-cemented soil or either actually pure ice deposits. And when the CO2 ice sublimation removes the grains, of course it exposes the ice, or the ice that was deeper and stable becomes closer to the surface, and then it sublimes. And then this involves lots of evolution on the ground. And that's what really carves the gullies, in my opinion. So I will of course almost say the same for the Christensen 2003 paper, to be honest. So really we have to be super careful with this idea that it's easy to have liquid water and make gullies. And also take into account the fact that on present-day Mars we have evidences that gullies are made by sublimating CO2 ice like minus 30 C, and there is no liquid water involved.
Yeah, okay, lots of good comments, and I don't think it's easy to have liquid water. I think, though, one thing that's super important is to separate CO2 ice from H2O ice, because the CO2 ice isn't going to be around at the time that the H2O ice is melting. I agree that the sublimation of the H2O ice is this flux, right, that effectively is going to cool off the system and making it harder, but I don't think that the gullies are consistent morphologically with CO2 ice in any way. I don't find those arguments convincing at all in terms of the morphologies. Furthermore, it's not possible to explain the salts without invoking liquid water. That's not going to be created by CO2 ice. And so I think this will be a key point of debate, is reconciling some of the geologic observations with what's possible from a modeling perspective. I really think looking at the ice and also considering what's going on in the interior of the ice in terms of what happens with dirty ice and the melting within ice where it's not in communication with that surface layer is really important, and something that's observed at temperatures lower than the freezing point in Antarctica and such for coarse grain-sized ice that has dark materials within it. So it's hard with the surface conditions to melt ice, but I think we need to bear in mind those special conditions that could allow it. It's a good point for discussion. In terms of what happens with dirty ice. Okay, thank you.
Sorry, send Bruce back to his seat. Pick our speaker. It was going to eat right into your time director.
At temperatures lower than the freezing point in Antarctica.
So Jim Hedges is going to now tell us about the hydrological systems in the cycle.
Grain-sized ice that has dark materials within it. So it's hard with surface conditions to melt ice, but I think we need to bear in mind those special conditions.
Ah, yes. Okay.
It's a good point.
Okay, great. Thank you. Thank you very much. It's a great pleasure to be here. And first, I want to acknowledge Bob Haberly and Francois Forget, who over 20 years ago invited geologists and other non-atmosphere modeling people into the community. And I really think over the years that's proven to be an incredible learning experience for us and hopefully for everyone. So today I want to talk about a combination of those aspects, which is indeed combining the work of a geologist, Robin Wordsworth, an atmospheric modeler, and Jim Fasta, who is a ice accumulation and flow modeling expert. So basically here, we looked at the hydrological system. The whole point here is to help constrain the ambient climate and its evolution through geological time. And we adopted a Mars system science approach, which is basically an organizational framework for interpretation. And we looked at the hydrological system and cycle, atmosphere, hydrosphere, cryosphere, lithosphere, through Mars history, through the entire Mars history here, and we followed the water, familiar to everyone here. We looked at the characteristics of the hydrological system and cycle that would be illustrated here, and indeed their individual components of the system and the cycle, and the water reservoirs and also the relationship and their interconnectedness with time. For example, this is a vertically integrated hydrological system, rainfall, infiltration, groundwater system coming out on the surface and lowlands, etc. So the key here is that we took 4 overarching themes and questions that emerge from these multiple studies. And I want to acknowledge probably everyone in this room because we've utilized a lot of the data that has been reported individually for specific features from all of you. So thank you for your contributions, and we found them extremely useful in our work in synthesizing this information. So basically, the first question is, did oceanic scale bodies of water and sustained marine environments, for example, exist in the Mars past history? If so, how long and when? Okay, how long did they last and when were they? And secondly, all agree on the extensive evidence. You know, we've heard about this from Bethany and everyone else in the room, of course. Everyone agrees there's extensive evidence for the presence of surface liquid water forming things like valley networks, fluvial channels, lacustrine environments, open and closed basin lakes, and delta-like features, or fluvial channels, and so on. But the question is, what is the duration of these, as Bethany was pointing out? What is the duration of these water-related environments? Are they interconnected by a robust, vertically integrated hydrological system, and in fact, and cycle, and are they together capable of feeding things like a northern loaded ocean here? That's a complete water cycle, okay, in a vertically integrated hydrological system. So the third point was, how do the other elements of the geological record and history of Mars inform us about the presence and persistence of water, and secondly, the robustness and interconnectedness of the hydrological system and cycle throughout Mars history, okay? Was it horizontally stratified as it is today, or was it vertically integrated, or was it part of each during geological time? And we do this by looking at the presence and depth of groundwater, the presence of phyllosilicates and weathering rates, landform degradation, and the nature of the ambient climate. And the whole point here is what are the implications of these themes and questions for the ambient climate through geological time. By ambient climate, I mean the average climate over time that gets perturbed, but it's the basic background climate. So basically, evidence for northern lowland oceans. The 2 shorelines have been proposed. Contact 1, which is the late Noachian, early Hesperian, which is in the black line here. I'm sorry, in the yellow line, and the essentially contact 2, which is the younger one at the essentially younger boundary there, okay? So there's 2 late Hesperian, early Amazonian, contact 2, and contact 1's late Noachian, early Hesperian. Now, this diagram here is from the work of Scholes et al. And his colleagues who really mapped these out and examined them in detail in a 2021 paper. I encourage you to read that because it's an incredible assessment. And it shows, in fact, agreeing with a lot of other evidence, that actually a lot of the things that have been mapped previously as shorelines or deltas, et cetera, they don't actually fit an equipotential surface, even allowing for tectonic deformation and modification. And so that really cast doubt on the synthesis of the long duration standing bodies of water in the northern lowlands, okay? We found essentially no compelling evidence, positive evidence, shoreline locations, delta, et cetera, for the presence of long-duration ocean-scale standing bodies of water in the northern lowlands at either of these 2 times. The most compelling additional evidence against huge volumes of water implied by contact 1-2, contact 1, 110 meters global equivalent layer. That's 100 global equivalent layer. That's 110 meters of water spread over the whole surface of Mars, or with contact 1 up to 5,000 meters, 5 kilometers of water. The problem with both of these is, where did water come from? And indeed, where did it go? Where is it today? If it was there, it can't all be lost to space, but it can't be accounted for by the present polar caps or even the cryosphere. So those are big issues that we need to deal with here. The evidence suggests instead that any significant input of water into the northern lowlands would be very rapidly frozen and sublime, returning to surface cold traps like indeed the polar regions, and leaving a residual layer like the Vastitas borealis formation for the younger one. This is the work of Kreslowski et al., and it shows, for example, that it is essentially totally frozen over the course of just a few hundreds of thousands of years. So that, again, says we're not talking about beach balls and cabanas. Nobody more than I would like to see, shorelines and happy campers and people lying out on the beach, etc., but it just doesn't seem to be very real. So the evidence suggests instead, like we said, and indeed with contact 2 today, the hydrological system, we know today it's horizontally stratified, okay, like you see here, and indeed back into the essentially early Hesperian, the late Hesperian, early Amazonian, contact 2 is thought to have been formed essentially through a global cryosphere, which separates the surface from the groundwater system. And, a number of people, many in this room have called on cryospheric breaching mechanism to enable the groundwater to reach the surface, okay? And that's a plausible model. But in fact, it was a horizontally stratified hydrological system in the late Hesperian, early Amazonian, based on those models, et cetera. And Martin, Turbet, and others have shown, in fact, that should that come out onto the surface, the water flow, that it just, again, following the work of Kreslowski and others, that this event is, you wouldn't want to be standing next to the event when it came out, but it's a very severe weather event. But again, it freezes, snows out, and essentially moves back to the cold traps, as you can see in this area, this diagram here, at a very rapid, geologically rapid period. So, indeed, evidence for a robust vertically integrated hydrological system and cycle. The hypothesized late Noachian, early Hesperian ocean, contact 1, implies a robust vertically integrated hydrological system where you're getting rainfall, infiltration, migration, and essentially upwelling to create Mars-scale northern lowland oceans, okay? So this, in fact, would have indeed in this things like we've talked about here, evaporation, oceanic lacustrine water evaporation, elevated atmospheric water contents, precipitation, rainfall and snowfall, infiltration into the subsurface, and then surface runoff and fluvial channels where precipitation exceeds infiltration, and local staging and lakes and things like this, and then completing the cycle by having the groundwater system come out into the northern lowlands to feed the ocean. That is an integrated hydrological system and cycle, and that's what's visualized for, in fact, the Noachian Age ocean. So we analyzed evidence for the nature of all elements of a vertically integrated hydrological system, like I've described up here, and we found little support for robustness or interconnectedness of the various pieces, okay? This is an end-to-end model. Parts are debatable, but indeed trying to find the integrated hydrological system, the elements don't seem to connect, and that's critical for the oceanic waters fed by the groundwater system and essentially a vertically integrated hydrological system. So indeed, rainfall precipitation, as currently understood, predicted to be really low. Fluvial systems are immature and often do not reach the northern lowlands, so there are a lot of things going on here, but many of them just don't reach the northern lowlands. And basically the characteristics of fluvial runoff events, and this is work by Stuckey de Quay, in very interesting paper, I think it was 2021, really important because what they did was they looked at paired open and closed basin systems. The water filled one, flowed out, flowed into the other. It did not fill that and overflow. That sets a constraint on the amount of water, and one can get rates from that. In their paper, they did a really nice job showing, in fact, that most of these, the vast majority of these had runoff rates and event timelines lasting 10 to the 2, 10 to the 5th years, more like 10 to the 4 maybe. And so this is a short period of time geologically, as Bethany was pointing out. And so these are likely to be caused by transient surface events and conditions rather than a continuously robust source-to-sink fluvial system like is often predicted here in a vertically integrated hydrological system. So the apparent lack of this hydrological system on the basis of the data we've synthesized here during that period of time suggests instead that the hydrological system was horizontally stratified, much more like this than indeed like this, and this is back in the Noachian. In fact, when we take a look at this, it would imply that the cryosphere groundwater system is effectively not in touch with the atmosphere, and thus becomes a non-exchangeable reservoir. And this has really important implications. We're discussing with Bruce Schakowsky here. On the surface water budget, like Mike Carr and I tried to estimate in terms of the budget in a previous paper, but the evolution of the DDH ratio, because fundamentally you're not actually exchanging much, it's mostly related to, in fact, loss from the cryosphere, and that's a very low rate activity there. So what about the implications? Again, the observed early and middle Noachian very high erosion rates. So we have two issues here. One of them is the question of the erosion rates, and the second one is what's up with the phyllosilicates. And we take a look here, and we think some of the candidate causes, in fact, are related to the three major basins that occur in fact, the early to middle Noachian: Hellas, Isidis, and Argyre. In this interpretation, I mean, these are huge basin events. I think we tend not to think about them because, as opposed to the moon, where we think about them a lot, on Mars, we're fascinated with all the other evidence of the rest of the geological history. We had a lot going on. On the other hand, if we go back and look at this, those three basins are in the early to middle Hellas, Isidis, Argyre, and Isidis and Argyre in that order. And it had a huge effect, okay? I mean, Segura, Thun, Stakely, Haberle, Turbay, and Ashley Palumbo and others have modeled this, and it's a kind of a forgotten kind of thing in a way. It's critically important because these are huge events, okay? And on the basis, these charts here are from Ashley Palumbo's work, but indeed they reflect all the other work that I mentioned there too. Basically, the basins form essentially a major vapor condensation into the atmospheric condensation, and then essentially intense hydrological cycle in which rainfall lasts for decades, hot rainfall. And we think that based on the kinds of things she mapped out here with the Isidis Basin, that these could easily be responsible for the production of the phyllosilicates, the vast majority of the phyllosilicates. That's something we should discuss in more detail. So indeed, these are also transient, huge rainfall events, which we think partially to wholly explain the elevated erosion rates. So fundamentally then, in this interpretation, neither process requires the high erosion rates or the phyllosilicates, a long duration period of surface erosion and mineralogical alteration, nor, as often envisioned, that the late Noachian early Hesperian period be characterized by an ambient climate of significantly elevated surface temperatures and abundant water. So we find evidence for this, in fact, in the work that Bethany referred to. This is, in fact, distribution of clays detected from orbit, from Carter and Ellman, et cetera. And you can see the relationship to the three youngest impact basins, essentially Hellas, Isidis, and Argyre. And so we would argue, again, that this is a critically important element in the formation of the fundamental formation of the phyllosilicates. In addition, in a paper by Gordon Asensky, et cetera, seven of these terrestrial complex hydrothermal alteration environments exist in complex craters. And we know that the complex craters are all over the place. So these are in addition to the fundamental events associated with the huge basins. So there's, as Bethany was pointed out, there's plenty of opportunity for, in fact, lots of niches for life, activity, and resilience, if you will. So I would say at the end here, then, if you look here in this, then the high late Noachian, early Hesperian geothermal heat flux argues for, in fact, a relatively thin cryosphere, but one that exists in the earliest history of Mars, and the presence of geothermally warmed groundwater below the cryosphere that would favor further mineralogical alteration. So we have at least three different environments for alteration. One of them is the big basins, the second one is the complex craters, and the third one is, as Bethany pointed out in a 2011 paper, essentially the hot groundwater, the warm groundwater at depth. Okay, so the implications of this then, basically the likely presence of a horizontally stratified hydrological system and a global cryosphere since the late Noachian, after the big basins form, implies that the ambient climate was characterized by a mean annual temperature well below 273 K. So we're talking here something mapped by, in a classic 2013 Forget et al. And Wordsworth et al. Papers, you can see, you know, a 225 K mean annual temperature, which is a lot of Kelvin below, essentially, the melting point of water. So that seems to be where we are for that, based on this synthesis. And such a climate is likely to involve snowfall, precipitation, and accumulation, and an ambient warm and wet arid climate characterized by rainfall and infiltration and runoff is not necessary. So the lack of evidence for significant vertical water exchange through this, again, suggests that water on the surface was limited. The atmosphere was relatively dry, and surface water was primarily sequestered in cold traps, whose locations were dictated by both latitude and altitude. Water lost to space since the late Noachian would have been largely from surface, near-surface water ice reservoirs. So let me try to synthesize this then. Our current synthesis strongly suggests that early to middle Noachian, large impact basin formation, Helicis and Narjar, shown here, well before the valley networks here, that they were accompanied by transient torrential hot rainfall events that were responsible for both the high erosion rates and the phyllosilicate formation. As the climate returned to ambient conditions in the late Noachian, it was likely to have been extremely cold, way below 273 K, and the crust dominated by a global cryosphere, as we see here, horizontally stratified. The short duration transient periods of liquid water availability and an immature unintegrated transient hydrological system. So essentially, any northern lowlands sea ocean scale bodies of water would have been transient, freezing and disappearing very rapidly. We think that the Hesperian age hydrated sulfates are likely to be related to Valles Marineris in the equatorial region here due to the 8 kilometers of vertical offset there that is likely to release groundwater. And this would then be filling the basin with the sulfur-rich groundwater and formation of the interior layer deposits with the occasional escape into the northern lowlands. And any of these observed essentially Amazonian age scattered and local valley networks are likely false positives for ambient climate conditions. They're transient climate conditions, as Bethany was pointing out, with an MAT greater, what they're due to is local transient insulation melting, volcano ice interactions. We've seen that with Serranius Tholis and others, where the hot summit here melts snow and ice on the summit and it drains. And also hot impact ejecta interaction with surface snow and ice, as seen in the Leo crater ejecta, where in fact all the valley networks that are associated with those in the Amazonia come from the edge of the ejecta deposit. So the ejecta deposit formed on top of snow and ice, and it melted it and it flowed away. So basically here, I would say that during the 3 billion year old Amazonian, the ambient, as Bethany was pointing out, the ambient surface climate was cold and relatively dry. I think everyone accepts that. And we also know from the work of Jacques Lescar and others that the spin axis orbital dynamics, the Milankovitch cycles, were very active throughout, certainly Mars history, but more dominant in the Amazonian, because we see less activity from the big basins and other type of activity earlier in the history. And water is, in fact, polar water is mobilized and essentially transported towards the equator, creating tropical mountain glaciers, mid-latitude glaciation, and so on. And then as obliquity changes back to lower values, it returns to the poles. In summary then, the fundamental structure of the horizontally stratified hydrological cycle is locally to have been established here in the late Noachian, and indeed have remained structurally unchanged for the remainder of Mars history. And this is very controversial, but that's what the synthesis seems to be leading us to. And this would mean that we would have trends in increasing cryosphere thickness and decreasing groundwater abundance which is related to the overall thermal evolution. So Mars, indeed, is a one-plate planet. It's losing heat conductively with time, much like the Moon. The lithosphere is thickening as the lithosphere thickens. Essentially, it's incorporating groundwater, so groundwater is decreasing, and the cryosphere is increasing with time. And indeed, that helps to, again, isolate it from any subsurface water, from any surface activity, and escape to space. So I would point out that this synthesis leads to more questions, of course, than it does answers. And as science is always, I always say to my folks that when I mention that we uncover new questions every time it's like job security. Oh, it's job security, you know. I mean, every time we explore something, some new questions. Sounds more like job security than scientific advances, but hey, you know, it is what we do. So basically what we're talking about here, I think, is we have critical questions and themes to pursue in order to provide tests, clarification, refinements, and a rejection of the synthesis that we put together here. The first one is that we really need to understand the initial water budget of Mars, okay? This is the last one. And participating in partitioning and sequencing as a function of time in relationship to the ambient atmosphere. Secondly, a critical issue is the primary atmosphere. What's primarily accreted? What do the basins do? Sometimes people say they blow it off completely. And then the secondary atmosphere. What's the relationship between the primary and secondary atmosphere? I think that's something that's been largely ignored. And the depth of the cryosphere, global seismic data would be great to start with this and then work backwards, if you will, and then further research on short-term factors that we've talked about here in terms of surface temperature variation. So I will just summarize by saying there's a lot to learn, and I'll leave this last slide on, which is the biological implications, of which there's a lot, and I encourage people to think more about the Antarctic dry valleys as an example. Thank you very much. And the depth of the cryosphere, global stunned silence. Start with this and then work backwards, if you will, and then further research on short-term factors that we've talked about here in terms of surface temperature variation. So I will just summarize by saying there's a lot to learn, and I'll leave this last slide on.
I have actually got one. Hi Jim, I'm Lonneke Roelofs from Utrecht University. My question is not so much on what beautiful work you presented, but more a basic geological one. We have these three periods now that we've been using for quite some time, the Noachian, Hesperian, and the Amazonian. And I'm thinking, would it be useful in a way, because the questions are becoming more and more precise that we're asking, officially subdivide these three periods into eras? I don't know what your thoughts about that are, but I'm curious. My question is not so much on what beautiful work you presented, but more a basic geological one. We have these three
Okay, so
periods.
correlating these features with the geological eras?
Yeah, so I was thinking the comparison between the sort of subdivision that we've made for the timescale of Mars versus the geological timescale of Earth, which is of course much more precise and subdivided more. And I was thinking, if we are trying to answer these questions more and more detailed, if it's a useful thing to do to divide up the Mars geologic timescale a bit further as well, and not just late, middle, and early Noachian, but actually put.
Yep, that's a very good question. If I understood it correctly, that you're talking about comparing the Earth and Mars timescales and what they might inform us.
No, I'm kind of asking if you think it would be a useful exercise.
Can you move a little bit away from the microphone? That's good. Okay, sorry.
I was thinking if it would be useful as an exercise and also useful for the Martian scientific community to split up the Noachian further, for example, split up the Amazonian in different eras. So that, because what Bethany also showed and where you're showing, there's much much changes happening during these different periods. So maybe as sort of anchor points in time. Okay, now we call it something different.
Yeah, I think when one looks at the geological evolution of Mars in terms of the geological periods, I think it really is critical, I believe is what you're saying, is to link the geological characteristics explicitly to those periods. Now, I think another thing we should think about is that these were defined many, many years ago by Ken Tanaka and other workers at the U.S. Geological Survey, and they had good basis for doing that. But I think, as opposed to looking at those eras, as religiously, we should go back and look at the basis for those. Okay, I think that's the first order thing, and I think linking these geological features, I just would say one thing: Mars sample return. We need to get samples from Mars. We need to date these surfaces because we just don't understand the details of the middle Mars history. We have a chronology. It's based on comparisons of the Moon, modeling of a lot of things, and I think we're really woefully inadequate there. But so before we can really do Earth Mars comparisons, I think effectively we need to go back and examine the basis on which these eras were made, were defined. I think they're all good, but we need to understand that, and then also tie the chronology into absolute ages. And I think that those are critical. I hope that was what you were driving at.
Yeah, that is what I'm asking. Should we then come up with a committee for the Mars geologic timescale, just like there is one for the Earth one?
Yeah. And, we, in a way, this is when we'll be able to get real insights into what's going on the Earth, too, because, the problem with the Earth is we have radiometric dates in hand, but the chronology is, the number of samples and the number of outcrops is woefully inadequate, particularly for the first 10% to 20% of history. So my dream, of course, is that comparative planetology will really help us get insight into that in this manner. So I hope that's the case. Thank you.
Is to talk to us about
get real insights into what's going on the Earth too, because
the history of water on
the problem
Mars.
with the Earth is we have radiometric dates in hand.
Many co-authors, so I'll let you use.
The number of samples and the number of outcrops is woefully inadequate, particularly for the first 10% to 20% of history. So my dream, of course, is that comparative planetology will really help us get insight into that in this manner. So I hope that's the case. Thank you.
The history of water on Mars.
The Earth is we have radiometric dates in hand.
Many co-authors, so I'll let you use.
The number of samples and the number of outcrops is woefully inadequate, particularly for the first 10% to 20% of history. So my dream, of course, is that comparative planetology will really help us get insight into that in this manner. So I hope that's the case.
Those are my charts. So, while we're waiting, I want to start by agreeing wholeheartedly with at least one thing that Bethany said, and that is, Francois, thank you for organizing this conference. It is a great opportunity to it's a great opportunity, as Bethany said, to bring together people from different communities, and as Jim said. The other thing I wanted to start with was looking at what Bethany and Jim talked about. There's a theme running through it that I want to make a little more explicit than they did, and that is that the Mars environmental system is an interconnected system that includes everything from the deep interior, the shallow regolith, the surface, the polar caps, the atmosphere, the upper atmosphere, the interactions with the sun, and loss to space. And if we're going to try to understand the history of water or other volatiles, we really need to consider all these different aspects. For my talk this morning, I'm going to focus on the last 3 billion years or so of history, and in trying to bring together all the different components, we've ended up with a long list of co-authors. And if you go back to the paper that, on this topic that we just published in Icarus and read through it, you'll see what each one of them brought to the discussion. So you really need a multidisciplinary, interdisciplinary approach and group of people. consider all these different aspects. So I'm going to start with a little bit of a summary. I realize after the last two talks I don't quite need this, but I'm going to go through it anyways because it will all use the same timeline down at the bottom and lead directly into what I'm going to talk about. I've broken up the timeline into the different epochs in Martian history, and I'm going to go through each one of them briefly to talk about the implications for climate. Starting with the Amazonian and working backwards, we have the measurements today of a thin, cold, dry atmosphere. We have, despite that, a seasonal water cycle. You can see that in the lower right, driven by exchange with the polar caps. The water cycle, the dust cycle, potential water and erosion on the surface, all driven in large part by the changing obliquity, which is the tilt of the polar axis with respect to the normal to the orbital plane as it oscillates on roughly 10 to the 5th, 10 to the 6th year timescales. These seem to be the primary drivers of climate behavior and volatile behavior during the Amazonian. If we go into the Hesperian, we see the outflow channels that clearly were carved by water, crater lakes. I put Olympus Mons on here as a reminder that volcanic outgassing of juvenile gases did take place, although not at the rate that would dominate the behavior. If we go back further in time, there's evidence that the Noachian was a different environment, and we can debate, as we've been doing already, what fraction of time it was different, but we see valley networks, we see significant erosion, as you see in the middle image there with the scalloped edges and scarp topography on the inside of craters and degradation of craters, and just from the crater counting on the right, the removal by the end of the Noachian of basically all impact craters smaller than 15 kilometers suggests a very different erosional environment than what we see today. And then in the earliest period, formation of phyllosilicates and other weathering products. Shannon, you see I did work the word phyllosilicates into the talk. What I want to do now is get into the behavior during the Hesperian and Amazonian. And what I'm going to try to do is in this chart, in a series of overlays, give you a sense of what I'm talking about, and then I'm going to talk about each of the components of this integrated environmental system in a little bit more detail. So if we start at the present epoch, we can look at the rate of loss of gas to space, shown in the upper right, as measured by MAVEN. This turns out to be, at the current rates, not a significant process, but integrated over time, going back in time, a major process in the evolution of water. The polar caps, which supply water to the atmosphere, which supply hydrogen and oxygen to the upper atmosphere, that can be lost to space. If we go back in time a little bit, the solar extreme ultraviolet, the EUV, that drives loss to space, it photodissociates the water and the CO2 into O, H, and C that can then be lost. The EUV increases going back in time, and if you go back to the beginning of the Amazonian, it was almost an order of magnitude greater than it is today. And the oxygen loss rate that drives water loss rate was almost an order of magnitude greater. The end result of this increased loss back in time is that in the Hesperian there was much more surface water present than there is today. On top of the loss rate, you have the obliquity oscillations that at high obliquity put more water into the surface environment, take it away from the poles. The consequences of that play into understanding the Dorsa Argentea formation. This gets at the geology. This is a map out of Head and Pratt's paper from a couple of decades ago. The yellow is the Dorsa Argentea. It is interpreted as the remnants of an ancient, larger south polar ice cap. after the ice has been removed. One of the points we want to make is that loss to space at the larger loss rates 3 billion years ago would have been able to remove a lot of water from the Dorsa Argentea to space. The other consequence of this is that through time, with higher obliquity, you would have more water in the atmosphere, and that creates a larger region in which ice is stable as ground ice. So the most common situation that you may have had would be quasi-global or nearly global near-surface water ice. So Mars is really an icy planet, and we're seeing it during a somewhat anomalous time period. That's the story I want to tell. Let me go through some of that, and I'll start with the EUV constraints on loss of water to space. The figure on the left shows the amount of oxygen in the upper atmosphere as a function of the EUV coming in from the sun. The oxygen in the upper atmosphere is what can be stripped away. So the increased oxygen abundance in the corona at higher EUV corresponds to a greater loss rate. That loss rate can be extrapolated back in time using the known history of the solar EUV. This is the same figure I had before on the right, showing the oxygen loss rate. If you took the current loss rate and multiplied it by a few billion years, you'd get something like 1.5 meters global equivalent layer of water lost to space. If you integrate under this curve of loss, you get around 4 or 5 meters of loss to space, but that ignores coronal mass ejections and other solar effects like flares that can increase this to maybe 5 to 15 meters of water lost over the last few billion years. So that's one part of the story. The next is if you try to use D to H to look at the evolution of water over the last few billion years. This is a model that Nora Al-Sayed and I have put together, a simple box model where you have supply of water to the atmosphere during this time from outgassing from volcanism, lost to space, and then an amount of water at the surface. I'm not going to go through the details of the model, but it's constrained by the evolution of D to H over the last 3 billion years. And if you look at it in detail and allow all the variables to cover their full range, you would get an estimated amount of water loss of between 7 and 50 meters. And that means that there would have been possibly as much as 90 meters of water at the surface 3 billion years ago, 3.3 billion years ago. Again, that means a much greater water abundance during the late Hesperian. The effects of changing obliquity are important, as has already been mentioned. You're going to hear that, I think, as a common theme throughout the meeting. The figure on the left is from Jacques Lascar's paper showing the statistical distribution of obliquity values since it's chaotic and therefore unpredictable. The vertical red line shows the current value, and you can see that we're at an anomalous time period. The obliquity would have been greater than the present obliquity almost 80% of the time going back over the last few billion years. That means we're in a very anomalous time. On the right shows the amount of water sublimed as a function of the obliquity. There are a lot of models. This figure shows all the different models, so you can see the uncertainties on there. It's even worse than that because we don't understand the water cycle or the dust cycle at the present epoch, which makes extrapolating into the past somewhat difficult. The key result is that most of the time, with the obliquity being higher, there would have been between 10 and 100 times as much water in the atmosphere as there is today. We can't pin it down more clearly than that. Francois, I no longer see the timer. It has timed out. Does that mean I'm done? I get another hour, don't I? Since I can't see the counter until it goes to 0. Is that most of the time, the obliquity being higher, there would have been between 10 and 100 times as much water in the atmosphere as there is today. the effect of water in the atmosphere changes the stability of ice, but it also changes the amount of water that is lost to space. Because more water in the atmosphere, it's able to be photodissociated, puts more oxygen into the upper atmosphere, and that oxygen can be lost. The hydrogen is lost relatively quickly. Again, coming back to the Dorsa Argentea, Jim had estimated that it would have contained the equivalent of maybe 20 meters of water, global equivalent layer. That's got to be uncertain by a factor of at least a few, because we don't know the water to debris mixing ratio. But something on the order of 20 meters can easily be accounted for by loss to space, and it's clear that much of the water from the Dorsa Argentea could have been lost to space. At least some of it can be accounted for by loss to space. And in addition, at high obliquity, you get wider regions of stability of ground ice. This is the Leighton and Murray concept, where if the surface or subsurface average temperature is lower than the condensation temperature of water vapor in the atmosphere, it will diffuse into the subsurface and condense. The figure on the top here shows essentially the current distribution of where water ice is predicted, and this matches remarkably closely with the actual distribution of ice as measured from the gamma ray spectrometer and neutron spectrometer on Mars Observer. At 10 times the amount of water, which is at the lower end of the range at higher obliquity, you get a much wider distribution of ground ice. At 100 times, you would have essentially global ground ice, and you would have likely significant amount of surface ice. So I've got only a couple more charts here. This figure tries to show the point that I'm making, that if you want to understand the water, you've got to understand the exchange between all the different reservoirs, from the deep interior and juvenile outgassing associated with volcanism, to the shallow interior, the lower atmosphere, and exchange seasonally or on obliquity timescales with the polar caps, driving the upper atmosphere and escape to space. If you want to see how each of these processes can be constrained, each one of them has a lot of observations that we can now tie together. I'm not going to work through these, but if you look at your favorite piece of the system vertically and look over to the right, you'll see those things that can play into it. And then my last chart, my conclusions. Again, most importantly, if you take nothing else away from this talk, which is an indication that nobody will take anything but this next sentence away from it, you really have to take an integrated approach involving all the different components of the Martian environmental system in order to understand the history of water. It's important to look at each aspect of it to understand what the constraints are, but then you have to bring them all together. If we go back in time, second bullet here, the rate of loss of water to space would have been much greater in the past due to both the increasing solar EUV and solar flares and coronal mass ejections, and to obliquity oscillations, both of which would explain why there would have been more water in the past. The loss of water to space provides an explanation for where at least some of the water from the Dorsa Argentea formation ultimately went. There have been a number of recent papers and analyses looking at how the water was removed from it, but it doesn't say where it ultimately ended up. Finally, the greater atmospheric water abundance in the past, driven largely by the obliquity oscillations, would mean that there was global or quasi-global near-surface ice, and that would likely lead to abundant surface ice much of the time. Mars was clearly, throughout time, on average, a global ice ball planet. And if you think about it, the history of Martian water and CO2, as we've been describing it, understanding the processes that play into it, clearly has important implications for understanding climate on exoplanets, and of course for understanding potential for life. And I will stop there. Thank you. That would likely lead to Mars is clearly throughout time on
Hi, Eran Vossel, MD. I have a comment and a question. I will start with the comment.
Think about it. Again, just a little bit further from the microphone. There's a lot of distortion.
Okay, now? I have a comment and a question. I will start with the comment. The humidity values assumed by these models, I think, are a bit too high because they assume surface ice on the surface ice in the polar region, even for high obliquity. But as ice sublimate, it creates a lag layer which drops the loss rate. So even Forget and Shogoffer, we assume 10 times, I think, is too big. We will talk about it on Thursday. And my question is regarding the D2H ratio. Does it assume that the atmospheric D2H ratio represents the entire ice in the polar region? And if it does, what happens if this ice is very, very old, locking climate scenarios which is much less D2H ratio?
The question really gets at what I think is one of the most important unknowns in the system, and that is whether the D2H throughout the polar ice deposits is the same as what we see in the atmosphere or different. Right now, we see water in the summertime being sublimated from all the polar cap. We don't know whether it comes from the white stuff or the dark stuff. Either one is capable of supplying the amount of water we see. And we don't know what the D2H here versus here is. The ensemble average of D2H coming off the surface of the cap matches what's in the atmosphere, which it has to, but we don't know what the D2H at deeper layers is. I don't know any way to get at this other than to go and dig down below the surface in different regions, pull up ice and measure it. With regard to your comment, I agree with you, and one of the issues is, I'm trying to think now back to what the comment was.
The amount of humidity is too high because it assumes surface ice.
Yeah. If we try to extrapolate to other epochs, which I think is what we want to do with this, it's really difficult because we don't know whether the water comes from the white stuff or the dark stuff. The white stuff, if you look at the temperature and calculate the sublimation rate, it can supply most or all of the water we see. The dark stuff covers maybe only 1 or 2% of the surface, but it's at much warmer temperatures. If it has water ice at the surface, contaminated by a little dust, sublimation from that can also supply the water, the bulk of the water that we see in the summer. If we wanted to extrapolate to other epochs, it makes a big difference which one is supplying the water today or what the balance is in terms of extrapolating. So it's a really difficult problem.
I meant not for today, but previous epochs where the obliquity was 45, ice could not be stable on the surface, so it's much deeper in the polar region.
Yeah.
The amount of ice you get when you have a lag layer on top of it must be lower just because you have a diffusion barrier.
I don't disagree with that. Extrapolate to other epochs, it makes a big difference which one is supplying the water today or what the balance is.
Hey, Bruce. Bethany Ellman,
So
Colorado.
it's a really difficult. I think we've met before.
We have, yeah. Can you just say a little bit more in your talk about what you, for this period, meaning, Hesperian-ish, so 3 billion years onward, if you were to tell me the story of atmospheric pressure during this period, like what do you think it is? And how well do you think it's constrained? And I'm poking at this for a reason, which is kind of the late water part of the story that I was talking about, which is the fact that, probably the last episodes of Lake Gale were kind of at the beginning of this period, and then we do see these, streams with chloride, like ponds of chlorides, even kind of 2.5 billion years ago. So what do you think atmospheric pressure was doing at this time, and how well do we know that? And if we get rocks back from this time period, can we look at little inclusions? And how well do you think it's constrained?
Good questions. I think to get at this, you need to look at what the reservoirs for CO2 are that can be mobilized. We have 6 millibars in the atmosphere, give or take. The ice deposits that you showed some data pertaining to contain maybe another 6 millibars. And adsorbed CO2 might contain a couple of tens of millibars that could be exchanged. So that means that the amount of CO2 is under 50 millibars, or of order 50 millibars. It's not that easy. You can't put all of that in the atmosphere. If you change the temperature, you change the tilt, you're changing the temperatures of the subsurface, and that changes the amount of adsorbed CO2 in equilibrium with the atmosphere. So I think you'd have a hard time putting more than a couple of tens of millibars at most into the atmosphere, if that much. If you look at the models that half the people in this room have constructed, a couple of tens of millibars raises the temperature a couple of degrees. So I think there's a disconnect here and an uncertainty where we don't know how to explain the types of things you're referring to. Changing the temperatures of the subsurface, and that changes the amount of adsorbed CO2 in equilibrium with the atmosphere. So I think you'd have a hard time putting more than a couple of tens of millibars. Thank you.
Francois, do you have any announcements? Before you go to the coffee break, I've been asked to remind you, if you haven't uploaded your presentations, please do so using the link on the webpage. And we are in coffee break until 11 o'clock. Thank you. Let's take our speakers again.
Okay, we'll go ahead and get started with the next session on early climate modeling of Mars. So first up, we have Michael Mishna. Just so you know, we have about 13 minutes for talks and then about 5 minutes for questions.
All right, great, thanks. Okay, so 18 minutes for talking and no minutes for questions. No. All right, thanks everyone for having me. We're, I guess, in this session going to be transitioning now from sort of those broader synthesis talks, those overview, great overview talks we heard this morning, and kind of dive into more specific topics. And the one that I will be talking about today is some research that I've had ongoing with Alejandro Soto at Southwest Research and Gaia Stuckey-Dequay at MIT, looking at these very crater lakes that Jim Head spoke about earlier that can provide some constraints on paleoclimates on Mars. Thanks everyone for having me. So our overall objective in this work is really to constrain the global environmental conditions that would have allowed both the formation of and the persistence of these crater lakes, these paleo lakes on early Mars. And so I've thrown up here just a representative example of what this might look like. You had an impact, and then at some later time during a period of favorable climate, meaning a climate where you would have had warm enough conditions to enable precipitation, rainfall, liquid water flow, you can fill up these craters, and whether or not they are these closed basin or open basin crater lakes tells you something about the abundance of water that would have been permitted on the planet during that period of favorable climate. So the three things we're really interested in are understanding the availability of surface liquid in terms of its abundance, how much was there, its distribution, where on the planet was it, and its duration, how long did it last. And our approach in this work is to reconcile orbital observations or imagery with models of the ancient hydrology and of ancient climate. So we'll use some numerical tools like general circulation models to try to reconcile what those models produce with the orbital observations. And as a brief background for those of you who didn't understand the difference between these two types of lakes, on the left is an open basin lake, something like Jezero Crater, where you have water that can drain into a lake from a watershed surrounding or adjacent to the lake. And then there's a path for that water to get out. So the water will build up in the lake over top the rim and then be able to flow out. Conversely, a closed basin lake, as its name suggests, is closed in the sense that water can flow into it, but there's no clear path for the water to go out. And so the behavior of these lakes tells you, or the nature of these lakes tells you something different about the climate in which they may have been formed. So the allowable depth limit of each of the two types of lake can probe the overall water abundance at the surface. And here I asked ChatGPT if it could create for me an example of a crater on Mars with a lake in the middle of it, and it looks more like an above-ground pool. And especially, so on the left is the open basin lake, right? You can see how water is ostensibly flowing out. The right is the closed basin lake. The one on the left, like, it's not quite filled up all the way, so it's a little sketchy. I asked it then, please fill the crater up more, and it thought, and it added a little more water to it, and I said, no, please add water all the way to the top. And it thought, and it added a little more water, and I tried my best with the prompt to get it right at the edge there, and it spun and said, you have used your allowable image production for the day. Please come back tomorrow or subscribe for a service. So I said, forget it. I think they'll get the picture of what is going on here. So an open basin lake needs a minimum amount of water in it in order for the overflow to happen. If it doesn't get enough water, it remains a sort of a closed basin lake. So you need to have a wet enough environment to allow water to build up in that crater to overflow. Conversely, a closed basin lake needs a maximum depth to avoid that overflow. So it can't be too humid or too wet of a system for a closed basin lake, because if the water builds up and overflows, it becomes an open basin lake. So that's where the constraints between these two different types of lakes come about. You can get a minimum from one and a maximum precipitation from another. Tells us the relative rates of precipitation and evaporation over this interval of favorable climate that satisfies these constraints. And we use a term which we refer to as the aridity index. It's really just the ratio of precipitation to evaporation. And as I said before, climates that are too humid, so you have a larger P to E ratio, are incompatible with the closed basin lakes because you have more precipitation than evaporation, and it would overflow if it was too humid. And conversely, climates that are too arid, meaning you have more evaporation than precipitation, would be incompatible with the open basin lakes because water would evaporate more readily than it would build up and overtop. And as Jim mentioned, there are some examples of coupled systems that have both of these, and these are very handy to have because the open basin lake fills up, overflows, and that water then collects in the closed basin lake. So you know you had at least enough precipitation to fill the open basin lake, but not enough to then fill up the closed basin lake. So these are very handy to have on the planet. So from orbit, though, we cannot determine what this aridity index is. We only see the geometry of the crater lakes. We don't know how much precipitation or evaporation was actually occurring in them at the time. What we do know, though, is that there's a minimum value of this index, AI min here, which tells you, which is required in order for those open basin lakes, all of them that have been observed on the planet, and we're using about 100 of them across the surface, for all of them to overtop. So it tells you how much precipitation relative to evaporation you would have needed globally to allow all of those open basin lakes to overtop. Okay, so our aim is to model the varying climate conditions to find the aridity index at each individual crater lake location, to find, for all the open basin lakes, such that those model simulations of climate satisfy this minimum constraint. And we can do this for each individual crater, not just in a global or holistic sense. When we have these best fit conditions from our climate models, we can then constrain the allowable precipitation at each lake by the metric I was talking about before. We can solve for the value of precipitation there, which is found in this equation, which just sort of defines the volume of a lake as the sum of, or the difference between the amount of precipitation that occurs within the watershed and the lake itself, so water's coming into the system, and then water that is leaving the system due to evaporation, and that's coming from just the lake itself. And you can calculate then the total amount of precipitation that comes in, doing some numerical magic that I'm going to skip over here, and give you measures of the minimum precipitation value for the open basin lakes and the maximum precipitation value for the closed basin lakes. So in particular, for these coupled lake systems, it's nice to have both of those values because you can then try to constrain how much precipitation would have occurred at a single favorable climate regime of unknown duration. This is the value T that you see here in these equations. So there's some period of time over which the climate was great, rain is falling, evaporation's happening, and you're building up these lake depths. So that's what we're focusing on, is one of those particular optimal conditions there. And so we use the GCM to find these results. Oops. So the tool we're using is the Planet WRF model. This is a model I've been working with for quite some time. We've made some significant updates to the system over the past couple of years that I'm very excited about, and I just wanted to share those with you. We typically have been using this model in its Mars form. We call it Mars WRF, but we've now made it sufficiently generic that we have we can user define any sort of planetary system you might like, and it includes things like changing the stellar type. We can do tidally locked systems for exoplanetary studies and the like. So it's become a much more generic modeling system now. We've just recently added a multi-phase hydrological cycle, which means we're now capturing and modeling liquid water in the system, not just snow and vapor or ice, but we actually have liquid water in terms of oceans and lakes on the surface. So we're very much able now to model a full paleoclimate system on Mars where you would expect to have liquid water. We have convective parameterization in the model as well, so we do have liquid precipitation on the planet that falls to the surface and is really what allows us to do these types of models of the hydrology of Mars. We have a 5-phase single-moment microphysics scheme. Basically, that just means we handle vapor, we handle cloud water, cloud ice, and then snow and rain. So we get all the different phases of water in our model that we keep track of independently. We've also made some improvements to our correlated K model just to make it more efficient and better able to reproduce different types of atmospheric conditions. And lastly, we now also include an offline definition of the surface properties in the model. So you can actually, with our model now, basically draw what you want Mars to look like, Paleo Mars to look like, and the model will produce a representation of the surface conditions to give you ice or oceans or different topography, whatever you'd like. So it's become a very, very handy tool for us. And now we've got a lot more capability with this model than we ever did before. All right, so I'm leading up to our initial results here. And so how did we set up our study to do this lake model? Again, we're trying to cover a wide parameter space. We have the abundance of water, how much is there, the distribution of that water, where is it located? For example, is it in the Northern Ocean? Is it in the icy highlands? Is it somewhere in between, or both? And then the duration of this water. So we can look at how that water would be influenced by changes in things like obliquity, eccentricity, atmospheric pressure, and the like. Our baseline case is a 1 bar CO2 atmosphere, but we know that we've known for some time that 1 bar of CO2 is insufficient to allow liquid water on the surface. So we had to add a gray gas, which is basically just think of it as like just a cheat to kind of boost the global temperature of the system to get you above 273 K, which would enable a liquid ocean. We could have replaced this with, for example, hydrogen gas or some other trace gas that elevates the temperature, but we just chose this generic gray gas to do that. And then our model is about 5 degrees by 5 degrees, has modern topography, faint young sun, we use a intentionally dark ocean, about 6% albedo, and a bright surface of about 30%. It's a very bright surface. And a 42-degree obliquity, which is about the long-term mean value of Mars obliquity. And we've heard from the prior speakers that we're at a relatively low obliquity compared to the long-term. Okay, so our results, the results that we've been getting here, first thing I did was I was taking a look at what happens as you change the ocean volume. So changing that putative shoreline, or that shoreline of a putative northern ocean, I've changed it from anywhere from 4.5 kilometers below the datum up to about 2 kilometers. And on the left column where it says landmass, you can see in blue, that's the areas on the planet that are basically ocean or sea or water, liquid water. And the red is the land. So as you go from top to bottom, you see that the ocean's getting deeper and deeper, and you're filling in more of the northern hemisphere with ocean. If we look at the annual average column water vapor on the right, well, you can see that as you add more water to the surface, as you have a bigger source of water for the atmosphere, the amount of water vapor you get in the atmosphere increases, and that seems reasonable. The one thing I will note is it's strongly localized above the source, and this is going to be one of the key takeaways, is that it's very hard to get a lot of water away from the source of that water. We've seen this before in some other models, but you get a very humid environment over the ocean, but away from the ocean you don't get a lot of water. The left column here, landmass, is the same as the previous slide. Then the next two columns simply show snapshots in time of where we're finding liquid water in the atmosphere. So this is rain and cloud water, both in northern summer and southern summer. And you can see that rain is mostly found in our model in the summer hemisphere, and is also driven by topography. It looks like to us that areas of elevated topography is where you tend to squeeze out a lot of that moisture. We're seeing that in the middle column. The areas in red represent areas of greater precipitation. It's really almost orographically driven. And in the right column, you see southern summer. That big red patch is right around Hellas. So again, topography seems to be a driver, as well as the presence of a sea, a localized sea in Hellas. So our next steps, in summary, haven't really gotten to the point where we can connect this to the study that I was talking about earlier with the closed and open basin lakes, but this is leading directly into that. They can be used as proxies for the past climate. We have this new implementation of Planet WRF to simulate the early climate. Our initial results are encouraging. The physics are behaving. It's always tough to get new physics in a model to work for you, but they seem to be behaving. We've not yet mapped this to the crater lake population, but that is ongoing work. And to come, we'll be doing some of the icy highland simulations, paleotopography, looking at lower atmospheric pressures, and just taking some more time to fully interpret our results. So thank you very much. Our initial results are encouraging. The physics are behaving.
Okay, we have time for just a couple questions.
We've not yet mapped this to the crater lake population, but that is ongoing work.
Hello, Martin Turbet from LND. I have a question on the metrics that you propose, like the Pmin and Pmax, right? And I wanted to know what is the magic trick that you have in this formula to make the evaporation disappear.
Oh, the evaporation, good question. The evaporation can be written as a function of that aridity index. So when you rearrange it, the evaporation can be substituted with this aridity index, or the minimum value of the aridity index. So once we have those constraints from the geometry, we can sort of back out the evaporation term and replace it with what we know the system had to have in order to be globally consistent.
But then I'm not sure to get it, because the evaporation is supposed to depend on the temperature, which is something you will calculate in the model.
Yes and no, but if you Okay, this is it's a good question that is a bit out of my comfort zone because this is the work that Gaia has been focusing on. But basically, if you consult the paper here, the Stuckey de Quay paper, it explains exactly what's going on here. The evaporation is equal to the aridity index is the precipitation over evaporation. So if you have the precipitation value, if you have that aridity index, the minimum value, that is what equals the evaporation term. So you can swap that out and basically pull out the precipitation and solve for that by itself. If you consult the paper here, the Stuckey de Quay paper, it explains exactly what's going on here. You can
Hi, Michael. Shannon Curry. Nice talk. What data sets would help you understand results more?
Are you talking in terms of like orbital data sets?
What future data sets might help, or current?
For now, I think we've got enough information with the global distribution of these crater lakes that will allow us to get a first estimate of the distribution of climate across the planet. So rather than assume a globally averaged climate, the fact that we have these crater lakes found everywhere allows us to target in regions of enhanced precipitation, enhanced evaporation, and the like. So while I don't want to say that we never want more data, for this particular study, we actually have the observations I think that we need in order to do it, in order to solve it. What we really need is to get the data we would need is to get our climate model to be consistent with whatever available data we can collect, right? Trying to validate and verify your climate model is always essential to give you more confidence in it. So in terms of the lakes, I don't think we need any more information. In terms of getting the model to behave, any particular observational data we have would be useful. I don't want to say that we never want more data. For this particular study,
okay, let's thank our speaker.
The observations I think that we need in order to solve it. What we really need is to get the data we would need is to get our climate model to be consistent with whatever available data we can collect, right? Trying to validate and verify your climate model.
All right, up next we have Martin Torbet.
In terms of the lakes, I don't think we need any more information. In terms of getting the model to behave, any particular observational data we have would be useful. I don't want to say that we never want more data. For this particular study,
okay, let's thank our speaker. Just thinking about it. Next, we have.
I think it's going to be okay.
In terms of the lakes, I don't think we need any more information. In terms of getting the model to behave, any particular observational data we have would be useful.
Nope.
Thinking about it.
Okay. All right. Good morning, everyone. It's a pleasure to be here. So I have to admit that over the past few years, I've been slightly drifting away from Mars science. But François had a good argument to convince me to be here today to talk about some of the recent results we obtained with the model. One of them being that the result I'm going to present you today, even though they are not super recent, actually I've never really presented them in conferences. So I think the opportunity was perfect. So today, maybe can I remove this? Or? It's a pleasure to be here. Up. So I have to admit that over the past few years, I've been slightly drifting away from Mars science.
Great.
So today I'm going to discuss some results that we obtain either in the lab or in the climate models to better understand how the greenhouse effect of hydrogen could have explained maybe in more details the climate of very ancient Mars. So just to start with a little bit of context, there have been quite some works in the past 2 decades about exploring potential scenarios to explain how liquid water could have been stable early in the history of Mars. Some work focused on studying the effect of clouds in CO2-dominated atmosphere, CO2 clouds, water clouds. Overall, it doesn't work quite well. People explored the effect of meteoritic impact that could have warmed transiently the surface of Mars, but it doesn't work, as Jim mentioned it earlier, super well as well. Another option was to explore the effect of volcanism, and in particular SO2, H2S. There were lots of work on that, in particular a recent paper by Ashwin Broad in the room that explored that. And again, the results were not very convincing in warming efficiency. And so there was one proposal, I could call it the magic trick, if you want, for modelers, which is that maybe the climate of ancient Mars, the atmosphere of ancient Mars, may have been warmed by a magic molecule, hydrogen. The reason being, at least from my personal point of view, because this is the only molecule so far, whether it's produced by volcanisms or degassing after big impact, that is the only molecule that if we put it in the model, that can actually warm enough the surface of Mars to form liquid water on the surface. So, based on this, fact that so far only hydrogen mixed with CO2, this is the only way we can warm in the model the surface of Mars, the surface of ancient Mars. Then we explored in more details how does it work and what can we derive if we put hydrogen in models in terms of hydrological cycle and compare that with observations. For this magic trick to work, actually, we rely on a process that is called collision-induced absorption. So you've seen these terms several times in presentation before, and you probably hear it again. Essentially, in an ideal world where molecules do not interact with each other, you expect molecules like CO2 or H2 to absorb at very specific wavelength that potentially can produce greenhouse effect. But if you mix molecules together, for instance, a molecule of CO2 and H2O, as they collide close to each other, they will, during the timing of the collision, allow one or two of the molecules to actually absorb at wavelength where they are not usually supposed to absorb. And for CO2, H2O, it appears like the mix allows, in some conditions, to produce strong absorption that can potentially produce a very strong greenhouse effect when we apply this to early Mars. So what are the evidence? Well, if we go back a few years ago, this is all the data that we had. So only 5 years ago, this was all the data that we had on collision-induced absorption between CO2 and H2. So in 2014, when Ramses Ramirez and Jim Casting were the first one to propose this idea, they had to rely on the only available data that we had at the time, which was not CO2H2 but N2H2, which was not satisfying because we expect CO2, not N2. And so over the few years after that, this is just the CO2 windows for you to compare. Robin Wordsworth in 2017 did some calculations where he made a prediction of what this CO2H2 continuum absorption should look like. This is the blue curve here on the screen. But that's still no data yet. This is model prediction. So we went in the lab a few years ago to measure that. We put CO2 and H2 in the tank. And this is what we got. The data measurement for CO2 and H2 collision-induced absorption, on which we built actually a model, in the model which is in the black here, that explained the best the data that we had, and we could actually use that to make prediction at over wavelength of what should be the collision-induced absorption of CO2H2, which we were able afterwards, this is thanks to work from people in Grenoble, to actually verify experimentally, and I think the match is actually pretty convincing, that this prediction that we made is actually verified at over wavelength. So building on this model, something that is nice is that we can make prediction on temperature dependencies, which we will need actually if we apply this on early Mars, where temperature can vary quite a lot. And so we are able overall to produce, I think, pretty robust data set for collision-induced absorption for CO2H2, and that is now, only for a few weeks now, available in the latest version of ITRAN CIA 2024. So if you want to play with this data, just go on ITRAN website and you can download exactly the blue, black, and red curves that are shown here on this plot. All right, so now that we have this absorption term, we want to put that in the model, in our 3D climate model, and see, what it does. Well, to do that, we have been developing here at LMD and other French lab a model that is called, that used to be called the LMD generic model, and now it's called the generic PCM for planetary climate model. That is actually a three-dimensional global climate model that includes a lot of processes. In the context of early Mars, for instance, we have the hydrological cycle for water, but also the condensation cycle for CO2, with the formation of CO2 ice cloud that François here explored quite a lot in the past. This is the model that were used in the famous Forget and Wordsworth 2013 papers, and that have been used since then to explore many questions on impact, SO2, etc., etc. You will also see some talks by Maxime Maurice and Asena Kuzukan after that will actually use this model for different, scientific cases. But today I will focus on using this model to actually explore the greenhouse effect of CO2, H2 in the model. And so just to give you a little bit of context, what we did here is very similar to what Robin Wordsworth did in his 2013 paper, the IC Island paper, but we did three main additions. The first one is that we included the effect of hydrogen in the model, this collision-induced absorption greenhouse effect. We looked, because then in this simulation we are much warmer, then a bit like Mike Mishna did with his experiment, we looked at different water distribution on the surface, building on the assumption that we don't really know at the time where the water was. So cases with a very dry surface and cases with very large oceans. And last but not least, again, similar to what has been discussed by Mike earlier, since in this simulation we are quite warm, and the fact that water on the surface will be mostly liquid, then the main reservoir for water outside of the ocean are becoming the lakes. And so we had to implement in the model a strategy to simulate where the water should go in the lakes. And so for that, we got some inspiration from work by Yo Matsubara, 2011, that actually used the similar metrics that what Mike presented earlier, and that allowed us to converge progressively the water cycle, including the trapping of the water, the liquid water in the lakes. Just to give you a little example of what we are doing, we have implemented what we call the asynchronous coupling strategy, which was what was developed in the Wordsworth 2013 paper for ice, but here we do the same strategy for water in lakes. So typically you have a simulations of early Mars, 3-4 billion years ago, dense atmosphere of CO2 and H2. We start with the assumption that lakes are forming everywhere on the planet. Then we compute the GCM, the 3D climate model, and after a few years we can predict, based on precipitation rate and evaporation rate, where should the lake form preferentially. So we can use this lake model to predict, after one iteration, how should the lake grow in some places and how should they decrease in size in some places. And we iterate back and forth between this 3D climate model and this parametrization for lake formation. And as we go back and forth between these two models, eventually we get to converge both the 3D climate model, so the atmosphere, the cloud, etc., but also the positions of lakes, of liquid water lakes, on the surface of Mars. And with these simulations, we can self-consistently simulate, if you want, both the atmosphere and the hydrological cycle with self-consistent, a distribution of liquid water reservoir on the surface. So now that we have this converged simulation, we can look at what they tell us. For instance, we can start by looking at the surface temperature maps. So for instance, here I extracted a simulations with a dense CO2 atmospheres of 2 bar and lots of hydrogen, 15% of hydrogen. And what you can see, these are temperature maps. On the left, dry planet, on the right, very wet planet with huge oceans. That in both cases, if you put enough CO2 and hydrogen, not only you can warm the planet above the melting point of water, but you can actually get crazy high temperature on the planet. For instance, here you see on the left, on Hellas, you have temperatures that are on the order of 50 degrees Celsius. And if I put more hydrogen in the model, I will get even higher temperature. And this is, of course, something that we see, whatever the water reservoir size that we put in the model. Then, if we look at the metrics that the hydrological cycle tell us, we can compute things on the model, such as, for instance, runoff on the surface that you expect from rainfall. You can also compute the lake distribution, here that you see on the plot below. So the simulation here that you see are for large oceans, but we can also do that with very dry planet. So I will go back and forth between the two simulations. So we did a grid of simulations with many different amount of water, CO2, and H2 to look at the results. And the main conclusion was that by playing with the distribution of lakes and the amount of hydrogen in the atmosphere and also a bit of the obliquity, we can actually tune where the lake should form on the surface of the planet. For instance, you can see that the simulation here that you see are for large oceans, but we can also do that with very dry planet. Then you expect precipitation close to Hellas, and so it's very difficult to avoid having different amount of water, CO2, and H2 to look at the result. And the main conclusion was that an ocean over there. By playing with the distribution so first listen, the position of impact crater lakes and precipitation runoff can be tuned in our model, assuming various water reservoir size and position, but also atmospheric composition. Second very important aspect, you might have seen that on these simulations, there seems to be a latitudinal band of actually lakes forming on the surface of the planet. Actually, this band is very similar to the prediction that Robin Wordsworth made 10 years ago, not on the lake distribution, but on the ice reservoir distribution, which led to the icy island scenario. And for the same fundamental reason, you have adiabatic cooling, that when you have water vapor on the north part of the planet that moves on, that moves up, sorry, to the islands, then because of adiabatic cooling, this water vapor condense and precipitate in the islands. Well, for the same fundamental reason, then that explains not only the formation of ice in the islands in cold simulations, but also the preferential formation of lakes on the warm simulations. So second listen, the icy island scenario that our community have talked a lot about over the past few years actually also work in warm mode with water trapped in the liquid form in the southern island lakes. And so now I'm reaching the conclusion based on this work. First of all, we have provided accurate CO2-H2 collision and induced absorption. Now they are available in iTron. With this 3D simulation, we were able to show that similarly to what we show with the icy island scenario, again, you expect a preferential accumulation of lakes on the islands. And last but not least, this is the main message of this presentation. Since the position of lakes and precipitation forming on the planet seems to be very, dependent on where you put the ocean on the planet, we need to develop new models that can self-consistently predict not where the ocean were in the first place, but where they should form in the end in these simulations. And for that, we need to develop a tool that is called the planetary evolution model, and that many people are going to talk about from LMD in particular during this week. And with that, thank you very much. Forming on the planet seems to be very, dependent on where you put the ocean on the planet.
Really nice analysis. I'm impressed with the distribution, but you stopped one step short of what I think would be the most important result, and that is, does the predicted distribution of where you would get lakes agree with the actual distribution?
Yeah, so that's something we plan to do. So Alexandre Gauvin is going to talk about that. This is exactly the direction that we are aiming to right now. Okay, comparing, for instance, the prediction of... so we did it in the... the story is long, but in the archive paper that is... there is a paper on archive that describes all of this. And we did some comparison with the lake distributions, but what Alexandre is doing at the moment, Alexandre Gauvin, is going a step further by comparing, for instance, the distribution of open basin lakes versus closed basin lakes. And so, yeah, this is what we are trying to do at the moment. This is exactly the direction that we are aiming to.
So Bethany Ellman, University of Colorado. So thank you for the talk, and I'm really excited actually to see the analysis, the new work on the collision-induced absorptions. I think that's important for so many planets. So awesome. I would love to propose to both you and Michael sort of an alternative scenario to think about running the models for climate. which is, as I look at the data in the context of, what we heard this morning about the likelihood of large oceans perhaps not being so likely, both in terms of the volume of water and evidence for persistence of the water body. Also for the kind of the unlikelihood of very warm conditions for some of the mineralogy that we're seeing. I would love to see the exploration of sort of what it takes to get seasonal melt only. So that is like kind of a more a view where the present is a bit of a guide to the past. Like how much CO2 and or H2O do you need to just seasonally get the ice to melt and start running off, and what does that model look like? So I just want to toss that out there as an encouragement as the model gets to be awesome to run that sort of case rather than the very warm ocean-driven cases.
So in this archive paper that I mentioned, we did this experiment, and we can find cases where adding the right amount of H2 can put the planet, just in the right conditions, not to melt the full ocean, but just to melt the icy island reservoirs. And the cool thing with that, if this is this simulation they exist already, the good thing with that is like the amount of hydrogen that you need to put in the model to reach that state is actually much lower than the 15%, typically it's a few percent hydrogen in the model, which I think is much more reasonable if you think in terms of what is plausible in terms of source and sink for hydrogen. So we already have the simulations exploring that. Yeah.
Okay, thank you.
In the right conditions, not to melt the full ocean, but just to melt the ice.
All right. Thank you very much.
And the cool thing with that, this simulation exists already. The good thing with that is like the amount of hydrogen that you need to put in the model to reach that state is actually
up next, we have Azana Kuzakan.
It's a few percent hydrogen in the model, which I think is much more reasonable if you think in terms of what is plausible in terms of.
Exceptionally, Asana could not come at the last minute, so she has to give a Zoom presentation, and I'm not sure it will work right away.
All right, thank you very much.
The live stream doesn't work at all right now.
Okay.
Only Asana could not come at the last.
Azana Kuzakan.
Exceptionally,
Hello?
Asana could not come at the last minute, so she has to give a Zoom presentation. The live stream doesn't work at all right now. Okay. Only Asana could not come at the last. The live stream doesn't work at all right now. Asana, can you hear us? The live stream doesn't work at all right now. Okay. Only Asana can not come at the last. The live stream doesn't work at all right now.
Sorry, do you
Only Asana, can you hear us?
Yeah, I hear you. I don't know if you hear me.
Live stream doesn't work at all right now.
I hear the same message I use for these simulations. And yeah, we added the slab ocean model and the photochemistry on that. And here I'm just showing some surface temperature maps and the photochemistry on that. And here I'm just showing some surface temperature maps and the photochemistry on that. And here I'm just showing some surface temperature maps and the photochemistry on that. And here I'm just showing some surface temperature maps and the photochemistry on that. And here I'm just showing some surface temperature maps and the photochemistry on that. And here I'm just showing some surface temperature maps and the photochemistry on that. And here I'm just showing some surface temperature maps and the photochemistry on that. And here I'm just showing some surface temperature maps and the photochemistry on that. And here I'm just showing some surface temperature maps and the photochemistry on that. And here I'm just showing some surface temperature maps and the photochemistry on that. And here I'm just showing some surface temperature maps and the photochemistry on that. And here I'm just showing some surface temperature maps and the photochemistry on that. And here I'm just showing some surface temperature maps and the photochemistry on that. And here I'm just showing some surface temperature maps and the photochemistry on that. And here I'm just showing some surface temperature maps and the photochemistry on that. And here I'm just showing some surface temperature maps and the photochemistry on that. And here I'm just showing some surface temperature maps and the photochemistry on that. And here I'm just showing some surface temperature maps and the photochemistry on that. And here I'm just showing some surface temperature maps and the photochemistry on that. And here I'm just showing some surface temperature maps and the photochemistry on that. And here I'm just showing some surface temperature maps and the photochemistry on that. And here I'm just showing some surface temperature maps and the photochemistry on that. Radiation. But only 0.49 watt per square meter reach the top of it, generates O3 and trace O2. Even in a reducing atmosphere like ours, generates O3 and trace O2, so it can alter even in a reducing atmosphere like ours, generates O3 and trace O2, so it can alter even in a reducing atmosphere like ours, generates O3 and trace O2, so it can alter even in a reducing atmosphere, the copper generates O3 and trace O2, so it can alter in reducing atmosphere, the copper generates O3 and trace O2, so it can in reducing atmosphere, the copper generates O3 and trace O2, so it can in reducing atmosphere, the copper generates O3 and trace O2, so it can in reducing atmosphere, the copper generates O3 and trace O2, so it can in reducing atmosphere, the copper generates information for us to study later on in the lab if that UVC flux would affect the surface and if it will challenge the microbial survival. And also the inclusion of photochemistry slightly reduced the extent of the hottest region. So you can see the temperature maps on the left with photochemistry, on the right without photochemistry. And so it reduces the temperature gradient, and that's here in our case is due to the water vapor abundances, and only due to water vapor abundances. But the change in the mean annual surface temperature is still minimum, around 0.04 Kelvin. And we have the zonal mean here for the difference of surface temperature. And we can see it at 40-degree obliquity. The photochemistry mainly redistributes seasonally, so it's not a global mean. And it warms the summer pole by 5 to 8 Kelvin while cooling the opposite winter hemisphere. And the tropical impacts are minor, so they are less than 1 Kelvin. And this reflects a weaker seasonal insolation contrast. And again, when we put that in only ocean grids or only land grids, we can see that the effects is only like mostly strong on the land grids only, and not much affecting the ocean grids. And later on, we also wanted to do some studies about how life would affect atmosphere, not just how atmosphere affects life. So for us, we focus in the methanogens. So methanogens uses CO2 and hydrogen for their metabolism, and they produce methane in return. And as this methane doesn't have the same greenhouse effect like hydrogen, it is weaker. The total greenhouse effect changes. So we wanted to understand how that affects. So we did a semi-coupling in collaboration with Boris Sotre and our master student. So the goal was to define some parameters. So in our case, the pressure, surface pressure, and the partial pressures of CO2, hydrogen, CH4, and nitrogen. And all this information was given to the first in the 1D model, XOK we use for that. And that gives us a pressure and temperature profile. And we use that one then in a biological model to understand how, due to the metabolism, the composition of atmosphere will change. And this change of the new atmospheric composition was then fed back to the 1D model, and that feedback continue running until we reached temperatures below 273 Kelvin. And you can see here the surface temperature first increases because we have some production of methane that adds to the greenhouse effect. But as we continue using hydrogen, the stronger greenhouse effect, the Gauss, the warming doesn't keep up and it goes down, and it reaches around after 700 years, it reached below freezing points. And now we have also the prototype to do this semi-coupling with the 3D model. And it has the same system, same way of thinking. So again, giving the composition to the 3D model to get the first pressure temperature profiles, and then feed that back to the biological model and continue like that. And we don't have yet the results because we are still working in finalizing that model, but hopefully we will have some results soon. And just to make you understand why that was also how we also use all this in a lab. So we created a little early Mars in a bottle. There we put some basalt as a sole nutrient and a surface represent. We put some salty water in these bottles, and we filled the headspace with CO2 plus 15% hydrogen, and use the Methanococcus maripaludus as our life representative. And we put the bottles in the surface in a temperature where we know that it existed on Mars. And we use the same UVC radiation that we get on Mars surface to irradiate these bottles as well. And we followed up if they will survive all these conditions or not. And so to summarize it all, the ocean heat transport redistributes equatorial heat towards the poles and increases climate stability. And photochemistry slightly warms up the surface and builds up O3, and it enhances UV shielding due to O3. And simulated surface conditions remain compatible with surface liquid water. And from the lab also we saw that basalt substrates promote microbial colonization, biofilm formation, and mineral alteration, and it's enabling biosignature preservation. And Methanococcus maripaludus could survive these UVC levels that we simulated with the 3D GCM, and they continue producing methane, and they were UV resilient. And we also saw that combining 3D models with lab experiments offers a different strategy, a powerful strategy to explore life-climate interactions. It could be useful for Mars and beyond. And these results can support then later on the future biosignature detection efforts and also the Mars sample return. So that's it from my side. And I will now try to put the YouTube back on, because I don't hear you. I use for these simulations. And yeah, we edit the slab ocean model and the photochemistry on that photography. And here I'm just showing some surface temperature maps and the photochemistry.
Okay, great. If anybody has any questions.
I have a comment that I already told. Now, we could hear very well, but I don't know if she can hear me now. One of the conclusions is that ocean heat stabilize the climate, has an effect on the climate. And in fact, the finding that the ocean heat transport has no effect on the climate. And because it's super isothermal for fundamental reason, and she shows that the effect is super small, and I think finding in some way it has no effect on the climate according to her. I have heard that, but I will. If you have another question, I can type it on the chat.
I think one more.
Yeah, so Lonneke Roelofs from Utrecht University. This is a question for me, but also from the people I was sitting next to. How did you select the species to put in your bottle? What kind of criteria is it, and how realistic is it to pick a Earth species for such Martian experiments?
Well, I chose this species because we know that they are one of the earliest life forms on Earth, and they are anaerobic, so they don't need the oxygen. And it was the atmospheric composition was a very good one for this microorganism, and they are chemolithotrophic, so they don't need any other special nutrients, and we could just make them survive with the rocks.
Thank you.
I don't know if that answers the question.
All right, so we should probably move on, I think. So next up is Arihiro Kamada. Hopefully I said your name okay. One second.
Climate, so obliquity is important parameters to change the planetary environment. So obliquity modulates solar insolation, so which reshapes the atmospheric structure. For example, the temperature field and so water field, and precipitation fields, and then, so finally, so change the likelihood of the surface, so water distribution, for example, the body networks formation. So in present, but even in present day Mars, so Mars has an obliquity cycle with a short terms of obliquity cycle of 100,000 years, and a longer wave or a periodic wave of 1 million years obliquity cycle and eccentricity cycle. And the object, so we assume that the early Mars also have a same periodic wave of obliquity cycle. The objective of our study is to explore this objective influence on early Martian climate and the consequent formation of body networks using GCM. So in this study, we used Japanese GCM named Miroku, so to the dynamical core. And in our radiative transfer scheme, so we assume the 2 bar CO2, H2O mixing atmosphere with additional gas of hydrogen between the 0 to 6%. And our radiative transfer scheme so considers both H2O and CO2 cloud effect, and we assume that 75% of solar insolation in comparison to today, so 440 watts per square meter. And in our model, so we calculate the atmospheric CO2 condensation, sublimation, and the snowfall, and the surface sublimation processes, and we also implement the H2O cycle, so atmospheric, so condensation, advection, so rainfall, snowfall, and surface river activity, and ice sheet dynamics and thermodynamics during the simulations. And in this study, so to explore the obliquity effect, so we changed the obliquity between the 30 degree to 50 degrees over a period of 120,000 years. So, and in this study, so we used the pre-true polar wonder topography. So this is not the present day Mars molar topography, and we used this pre-true polar wonder topography suggested by the Borey et al. 2016, and we assume that lowland ocean, so with elevation below the minus 2.3 kilometers in this study. And we approximate the obliquity cycle using a very simple sine curve. So initial obliquity of 40 degree and obliquity amplitude of 10 degree, and the period of obliquity variation of 120,000 years. And in this study, to calculate a very long time scale of Martian climate evolution, first we run GCM, 40 months years, and then this output of atmospheric boundary conditions such as the snowfall rate and surface temperature are inputted in the ice sheet model, and ice sheet model calculate for 15,000 years offline. And then, so the ice sheet models output, such as the ice extent and the subglacial melting rate, are inputted again into the GCM, and we again calculate the GCMs, and the process is repeated during the once obliquity cycle of 120,000 years. So now let's move on the simulation result of our GCM. So this is the animation of the surface temperature evolution of hydrogen or non-hydrogen case and 3% hydrogen case, and the right one is the 6% hydrogen case. So surface temperature usually was higher in higher latitude during periods of higher obliquity case, while the opposite occurred during the period of lower obliquity case. At the non-hydrogen case, temperature was greatly below the 200, the melting point of water, so not supporting subglacial melting. And with the 3% hydrogen case, so middle picture, so temperature was close to the melting point of water, slightly below the melting point of water, so allowing for intense subglacial melting water underneath the ice sheet. with a 6% hydrogen gas, so light one, so temperature was much above the melting point of water, so it allows the liquid water, so surface rainfall and liquid water activity on surface. And this animation shows the evolution of the global ice sheet distribution of 0%, 3%, 6% hydrogen gas. So with a 0% and 3% hydrogen gas, ice sheet formed lower latitude during period of higher obliquity case, while the opposite occurred during the period of lower obliquity case. So with a 6% hydrogen case, so light one, so most of the precipitation is occurred in the form of rainfall, and ice sheet only distributed around the southeast region. So these regions, so the surface temperature is slightly below the melting point of water, so it promoting the accumulation of ice sheet. And so 6% case, so most of liquid water rainfall and snowfall occurs. And this figure shows the global evolution of surface river activity during the one obliquity cycle. With a 0% hydrogen case, only so near shoreline regions river activity occurred. These waters come from the subglacial melting subglacial melting water. And the 3% case, so river activity is more active. So in comparison with 0% hydrogen case, this water is come from the subglacial melt water beneath the ice sheet. And the 6% hydrogen case, so river activity is more active, and this most of water is come from the rainfall. And in the region of southeast region, so this water is come from the subglacial melting. So then we compare our modeling river result with the observed valley network system. So green color shows agreement with valley networks and agreement between our model and observed valley networks. So with non-hydrogen case, only 5% valley networks is consistent with observation. So however, in the case of 3% hydrogen case, so during the period of one obliquity cycle, 50% of valley networks could be produced by the subglacial melting activity, subglacial meltwater activity, and 6% case, more than 70% of valley networks could be consistent with our model and observed valley networks. It is due to the combination of rainfall activity and subglacial meltwater activity. Yes, and this is the discussion and summary. Because obliquity changed solar insulation and the atmospheric structures, so the distribution of ice sheet and rivers became more extensive in comparison with the fixed obliquity case. So regarding the formation of valley networks, so 3% case, 53% of valley networks is very consistent with observed valley networks. This value is higher than the fixed obliquity case, so 49 cases. So there is 4% increase. And with a 6% hydrogen case, so 72% of the valley networks could be explained by the rainfall and subglacial meltwater activity. And this value is also higher than the fixed obliquity case. However, in our model, we cannot express remain 30% of observed valley networks. So in future, we want to know the cause of other valley networks. Thank you.
Okay, we have just a couple minutes for any questions.
Hi, I'm Vos LMD. Very nice work. I was wondering how sensitive is your model results to the geothermal heat flux sensitivity?
Geothermal?
Heat flux.
Yeah. So, yes, so of course, So in our study, so we used the geothermal heat flux of 55 milliwatt per square meter. So as you say, so geothermal heat flux can affect the subglacial melting rate. So if we assume the more intense geothermal heat flux, this value increase more, but so several percent increase, I think, yeah. So the sensitivity of geothermal heat flux is studied on my 3 years ago paper. Yes.
Bethany Ellman, University of Colorado. Thank you for the talk and the very nice work. I like the approach a great deal. Talk about the characteristics of the ice sheets. Are they pure ice? Are they dirty ice? Do they have a fixed grain size? And does that matter? It looks like it does in some ways, but how sensitive is it to the choice of some of these ice sheet parameters?
Yeah, so we assume, so we assume the pure water ice, so the melting point of ice is 273, and yeah, pure water. And we assume the same parameters to the terrestrial ice sheet model. So in future, we should explore the sensitivity, parameter sensitivity of the ice sheet model. Yeah, thank you for your comment.
Okay, so now is lunchtime until 2 p.m. I encourage you to compare notes on various boulangeries around town, and we can see who thinks they have found the best, or cafes, whatever you prefer. So yeah, the next session starts at 2. Thanks.